So that's not so hard. So you see, if we define this mu I plus p and zp, I just define is just zp and this function. So anyway, this is continuous even it's locally constant, right? So if we defined like this, so let's see, if fk, fn is I0 to pn minus 1, f of I 1, I plus p n zp. And then fn, we know, goes to f, so converges to f uniformly. This is locally constant functions. Okay, so if we just look about measures, if mu is a measure, I just want to avoid the trouble about distribution because the limit may be maybe a little bit more complicated. So if mu is a measure, let's see the Riemann sum, and then f n goes to f anyway uniformly. Okay, converge to this. So what do you get? You get this n goes to infinity f n mu. You can exchange the integrations and Fn mu. So this side is just f of mu. But this side, what is this side? This side you can plug in this. So is limit n goes to plus infinity I 0 p to the n minus 1 f of I mu I plus p to the k zp. Okay, or p to the n zp. So you see, this is really a Riemann sum. You going from a Riemann sum, you get the integrations. So so that's how you get it. And even we can have more like proposition. So if mu is additive, bounded function on compact open subsets of Zp, say like all these functions on all these subsets, and then what do we have? Then mu extends uniquely to a measure on Zp. Okay? So how do you extend it? You just use this formula. You just define the integration by this formula because you can take limit. Okay? So that's a Riemann sum we can have. That means the integration is really an integration, just like ordinary analysis. Okay. Now the rest of the talk, or this talk, today's talk, we'll talk about examples and actions. So maybe section 2.3, maybe this one should also contain in here. So examples and actions of measures and distributions. So first, let's give some examples. The first thing, let's look about harm measure. See, so harm measure. What is the harm measure? For harm measure is invariant under translation, right? So if mu Zp is 1, just like Zp, just like this, then we have to calculate this mu I plus Pn Zp is 1 over Pn for all n. But you see, this is not bounded. This is not bounded because this in p-adic analysis, this is huge. This is not goes to 0. This goes to huge number. So it's not bounded. So that means no harm measure. And I think many of you know the result from like the classical books of Lang or Washington or all this, right? So no harm measures. Okay? So this one is not a real example, but the second one we have a real example is Dirac measure. So we write down as delta A. So A is contained, say, in Zp. Yeah. So what is the Dirac measure? So we just define f delta A. I just define as f of A. Okay. So that's the Dirac measure. So if we studied in the main theorem, to know a measure, you just to know its Amis transform, to know its power series. So let's see what is A delta A t. So this is n bigger than 0, Tn Zp f delta A, or Axn delta A, right? But you see this is nothing but, or you can say 1 plus T x delta A. Now you just take this x to be A. So it's just 1 plus T to the power A. Okay, so this is the power series. Even A is contained in Zp, but certainly if A is contained in N or in Z, you can say this is the power series. Okay, so that's the Dirac measure, and actually so this one is used everywhere. Okay, now the third example I want to say is in my notes. Is basically is in the notes in the chapter 2. I will not talk about chapter 2, but I will talk about this measure. So this is this lambda A in my notes. Okay, so here I have A is contained in Zp cross. So A contained in Zp cross. To define this measure, I actually first get it from its Amis transform to get it. So A lambda A t, I just get is 1 over t minus A over 1 plus t to the A minus 1. This one you can see, this is actually from cyclotomic extension from this global units. So you can get this. And there are lots of explanation about this. But you just from here, you can see, because this have a residue, so have a simple pole as t equals 0. But this one you can also have a simple pole t equals 0 and the residue is 1. So you minus it. This is actually is contained in here. So this is Bn Tn n bigger than 0. Bn bounded. Okay. So if you take this power series, you get a measure, and this measure we call the number A. This measure we call number A. So in my notes, we actually proved this ZP xn number A is this, is -1 to the power n, I think. 1 minus A, 1 plus n, and zeta 1 minus n. So you see, this is related to the valuation of z functions at the negative integers. Okay, so from this one we can actually deduce. So from this, so we can actually deduce Crumer's congruence theorem. So, or you can actually also define p-adic z functions. Okay. So this measure, because you can see, yeah, you get z values, z functions. So that's interesting, right? So that's the one we have. So this is a measure. We have a Dirac measure on this measure, and then let's have another called Kuberta-Leopold distribution. So again, so we have mu, we call mu KL. Again, at first get its Amish transform, so A mu KLT. I just get is just log 1 plus t over t. So this one, what is log 1 plus t? You get this Taylor expansion of log 1 plus t, okay? And then you can see this is not in E plus, but this is in R plus. Okay, so this is in R plus, and this one is a distribution. This is a measure. But this distribution, you can also see this ZP xn mu KL. You can find this. This is nothing but a minus 1 n zeta 1 minus n. So you get the interpretation of p-adic function as z functions at the negative integers. So you see, this one is even better than this one, because this one you have an A, and here the right hand side is independent of A. So that's why sometimes distributions, you need to use distributions instead of just measures. Okay, so these are the examples, and this example I also used in the notes chapter 2 about p-adic z functions. Okay, but it's a different way to do it. So these are the examples I'm giving. So now I move to some actions. So now the first example now is actions. So first action, what I want to do is multiplication. So it's by G. So of course we have, for distribution, you can say D is in GA. For measures, G is in C0. Okay, it just depends. It's the distribution measure. So we just define this ZP F. So if we have a measure G mu, we get the new measure because we call G mu is just defined as FG mu. Okay, we just define like this. this is also just like in analysis, you have Riemann integration, you have Riemann-Stiegler integration, I think. Yeah. So it's just like this. So for this, we can get it's just some more examples. If gx is just x, this you can compute. So you can compute this ax mu t. So if firstly you have mu and then you have x mu, so it's different, and this is nothing. You compute it. So 1 d over dt a mu t. Okay. So this like this kind of power series. If you are familiar with cyclotomic fields, you have this Coleman power series, and the Coleman power series can all be re-established using this machinery. Okay. And, so this is ax mu, and if gx is just zx, so we say v pz minus 1 is bigger than 0. So we can get a zx mu is just a mu 1 plus t z minus 1. Okay. So if g is this, is a, for example, a plus p to the k zp, then that's what we get restriction. So we call g mu, we call restriction of 1 plus a plus pk z. We call this. Okay, and this one you can get is a restriction a plus pk zp mu t is p to the minus k z p to k is 1 z minus a mu 1 plus t z minus 1. Okay, so to prove this, the third one is coming from the second one because of the identity we get about this function and all this function of this. Okay, I give before, and I think for this one it's very easy. You can prove. You can just get this. Say if you get a mu t something and you just try to compute a x mu t, and you should get this. Okay, so I will leave this if you try to compute it yourself. Okay, so this is just multiplication. The second thing is phi and the Poisson action. So in E and R, we just define this t goes to 1 plus t to the p minus 1 is phi action, and we defined in a complicated way about this Poisson action. So here we can define this phi action and Poisson action quite neatly. So what is phi mu? So if we dp f of x and the phi action on mu, I just define as zp f of px mu. Okay, so and the Poisson mu zp pzp f of x over p mu. Okay, so this is phi and Poisson action. Looks very neat. Now you need to define it to recover what the actions of phi and Poisson. So let's see the property we need to find. The first thing you can see is a phi mu t. What is this? We know is n bigger than 0, t to the n dp px n mu. But this one is just a mu 1 plus t to the p minus 1. Okay? So you see phi is really an action t goes to 1 plus t to the p minus 1. So this is a phi mu t. Now let's see the property about phi and psi. So recall we have psi times phi is identity. Now let's check this, if this is true. So let's see, if we have Vp f of x, psi phi mu. So first we need to get the psi action, right? So it's just p Vp f of x over p phi mu, right? But then what is p-Vp? P-Vp is just the restriction at p-Vp, right? So if this should be Vp is 1 p-Vp of x, f of x over p, and then phi mu. Okay? Now you just take the phi action. Now it's just Vp, and this whole function if you take the value at px mu, but if this function you take the value at px, you get this is nothing but f of x. So this is nothing but f of x. So you actually get, so that's how you get psi times phi is identity. Okay, so this is first property you can check. The second one you can check is psi mu is 0 if only if mu has a support on GP cross. So that's easy, because if psi mu is 0, just means this side is all 0. That just means on over PZP this is 0. So just means mu must have support in PZP in ZP cross instead of Z, because it's 0 on PZP. Okay. So the third thing we can check is the restriction of ZP cross mu. This is 1 minus phi mu, phi psi times mu. Okay, so this is also an easy check. Let's see. So Vp f of x 1 minus phi psi mu. So this certainly is Vp fx mu minus, so Vp f of x, so it's fp of x psi mu, right? Because by the definition there, so this is Vp f of x mu, but this psi is just, you get pVp f of x over p, so you get f of x mu. So that's ZP cross, because ZP minus pZP is ZP cross f of x mu. So that's the identity we need. Okay, so 1, 2, 3. We have all these identities, and from these identities we can get the formulas about psi mu. So the corresponding formula you can get is, so psi f 1 plus t to the p minus 1. So this is psi phi, right? Psi phi. So this is ft. So this the first formula. So if f is a mu t, so you get this. The second one is just say you have if ft I is 0 to p minus 1, 1 plus t to the I, f of I, 1 plus t to the p minus 1. Okay? You can see, like, if I is not 0, then this is just sum of all these Dirac measures. And then this Dirac measures has support is not on ZP cross, has support on ZP cross. So that means psi ft is just psi f0 1 plus t to the mu t minus 1. Because for all others, the support is not, the support is on ZP cross. Except this one, this support is on ZP, PZP. So, but this one is just f0t. So that's why you have this. This is the same thing that we define as E. When E and R, how do you find this sign? Okay, and also the formula for, we just have the formula for multiplication of I plus P and ZP, the restriction. And this one, what is this? This is certainly is just the sum, right? I equals 1 to p minus 1 restriction I plus PZP mu, right? And we know the Amish transform for this, so that we know the Amish transform for all these. So from here you can get, psi phi psi f t is just 1 over p zp equals 1 f 1 plus t to the z minus 1. Okay, so that's how we get this one. So this kind of property is just the one we really expect from this E and R. So that's why we really can make very explicitly here about in our measures and distribution how the phi and the psi action. Okay. So this is the second action. So the third action is this gamma action. So it's gamma action. So now gamma, you always remember, is just say we have QP, you have QP with zeta p infinity, and then you have QP bar. Okay, so this we call it is HQP, and this is gamma QP, or you can just write it as gamma, and this is GQP. Or if you have K, and there is a K infinity, is just K, or this, adding all this, or sometimes I use theta, sometimes you have to use mu. Okay, but it's the same. Or you have K bar, this QP bar. So this is GK. Or this is HK. This one is gamma K. So we will always use this. So we have this gamma action. So chi is gamma goes to ZP cross. So this is cyclotomic character. Or sometimes even more you have GQP. We can also call this a cyclotomic character. from here, so take the quotient to gamma and then map to dp cross. Okay, so those cyclotomic characters. So now this one is the, so f of x, some gamma mu, or action on mu, is action on mu. There is just Zp, so f, I think chi gamma times x mu. Okay? So this is an element in Zp cross. So this is an element in Zp, so it's still an element in Zp. So you get this. So this is a gamma action. Now you can check it easily. The action of phi commutes with gamma, and the action of psi also commutes with gamma. So the actions of phi commutes with gamma. So this is easy to check. Let's check it. So let's see. Zp f of x phi gamma mu. So this is Zp f of px gamma mu. And then Zp f of p, so chi gamma x mu. Okay? Or you can write down more. So it's f chi gamma x phi mu. So it's f of x gamma phi mu. So you see this commutes with phi commutes with gamma. And the same thing you can see psi commutes with gamma. Right? Okay? And so what is the Amish transform of this gamma mu? So now you can check this. So A gamma mu T. So it's just A mu 1 plus T to the chi gamma minus 1 is gamma A mu T. Okay? But this, I think this is not so hard to check. Okay, let's see. Tn Zp xn mu, gamma mu. So Tn so it's chi gamma times x n mu. Okay? So now you just need to see this is actually the same. Or if you don't mind, you can write down this as this is Zp 1 plus T x gamma mu, and then 1 plus T chi gamma times x mu. Okay? And you will get the same. So that's why the gamma action is really from T to 1 plus T to chi gamma minus 1. So in tomorrow's lecture, I will tell you why. So in another setting, okay, it's in this really the theory of phi gamma module setting. Okay, so we've already studied all the actions, multiplications, phi actions, and gamma actions. Now we need to know these convolutions. So convolution, so it's just if we have two distributions or two measures, we want to multiply it together so we get another distribution or another measure. Okay, so that's the product. If you really want to say it's just product. Because in the proof of the main theorem, we didn't say it's a topological, so it's a topological isomorphism, but it's not as a topological rings. But now because of this, we're going to be a topological ring. And you can have the identity element too. Okay, so what we want to say, we define this ZP f of x lambda times mu. I just defined as this. So it's ZP f of x plus y mu x lambda y. Okay, we just define it like this. So first you want to check this is well defined. So we define this. So well defined. Why this is well defined? So that means if fx is in LAH, let's see, if f is in LAH, because if it's a distribution, we need to use a locally analytic function. Then for y0 plus ph zp, what do we get? We get in this area, f of x can write out as a Taylor expansion of this. The f of x plus y is just this, because f is in LH, so you can write it as p(n)h f nth derivative at x plus y0 and over n factorial times y minus y0 over p to the h to the power n. So we're going to get this. But this one, see, this certainly is in LH, so this is contained in LAHX, LAHY. Okay, so this is an analytic function, locally analytic function, and this is also locally analytic function. So you can see this is contained in here. So in particular, you get VLAH of this whole thing inside pnh f nth root of x plus y0 over n factorial. This whole thing goes to plus infinity as n goes to plus infinity. So that means you can really have, so this one inside is really an analytic function, okay? Or maybe in this one we need a mu y, mu x, lambda x, okay? So this one is well defined, okay? You get a good one. So this is for distributions. For measures, you can get the same thing. And it's easier because if f in C0, because if for measures you must use continuous function, and now you see this function, then this x goes to Zp fx plus y lambda y. This is C0. because, or this is mu y, okay? Since f is uniformly continuous. Because it's uniformly continuous, and then you get this is still continuous. Okay? So this is the theorem in analysis. So this is in C0, so again this is well defined because this one is a continuous function, so you can also well define this. Now because of this, you just check. Want to see this convolution, you just check a lambda convolution mu t is a lambda t a mu t. Okay? And this, for this you can check, like you can pick some text function like zx and zy. Okay? As I did in the notes. Okay? So you just check this. And now you can see what is the unit here. The unit here is, so you can delta 0 I think, yeah, delta 0 is corresponding to 1 plus t to the power 0. It's just 1. Okay, so you can get this. So delta 0 is the identity, and you have this. And also you can see also the Fubini theorem is also true. So it really doesn't matter it's lambda convolution mu or mu convolution lambda, because the product is the same. Okay, so that's the convolution. Also you can say is a product. Okay, so the last thing today is I want to say about this is a special action on distributions, but not in measures. So it's called derived distributions. So for the distribution, you can actually take some derivatives. Okay, so I just define f d mu. I just define dp f prime mu. Okay, so that means that this is because if f is locally constant, then the derivative is still locally analytic. Then the derivative is still locally analytic. Okay, so analytic function, you can take whatever derivative you want. So you can get this. For this one, you can get a nice formula too. So a d mu t is log 1 plus t a mu t. So you just take a log. Okay, but this log again, you need to think of this log as t minus t over 2 plus t squared over 2. You need to think as a power series like this. Okay. So for these two lectures, so in summary, for these two lectures, we just studied basically this. Okay. So we studied this C0, ZPL. We studied this LAH, ZPL. Then or this LA, ZPL. See? And in this side, in the dual side, we studied this D0, ZPL, this measure. And this is D, ZPL. Okay, so we have the inclusion from here includes here, and so that means from here to here. So we have here is a Marley theorem. Marley. We also have locally constant. Basis. So basically that's what was C0. For this one, we studied this Amis theorem. So it's about description of f ANF xn in LA. So that's what we studied here. And in this side, we did an isomorphism of this to R plus, this isomorphism of this to E plus. Okay? This side is called Amis transform. Again, this is Amis transform. In fact, what we didn't study is, just like in the classical case, we have C0 is just a continuous function, and also have like differential functions of degree 2 or degree 3 or degree R, right? Have a smooth, have a continuous differential of the R's derivative, something like this. So in fact, here we also have this ZCR, something like this. And here you can also have dr, and then you either have this kind of picture. So this is just dual to each other. This is dual. This is dual. But this one, this is much more complicated to study these CR functions. For the general picture, we think these two and these two is good. And also we studied the main theorem. We related all this to the E and R, the Roba ring, and also the, should say, you can say this Fontaine ring. So next talk, I will talk about why this E, why this R. So how do you get this? So that's the theorem of phi gamma module of Fontaine, and that's a lot of work and more notations. So today we already have some notations, but then tomorrow we have many more notations. So I think today I just stop here. Okay.